Hello students, good morning and welcome to another video lecture of physics. Last के video lecture में we were discussing about a photoelectric effect, experimental study of photoelectric effect, right? We have discussed what will be the effect of change in intensity of incident light on emitted electrons, photoelectric current, stopping potential and so on, right? In the same way अगर हम frequency change कर रहे then what will be the effect, right? So something like this we have already discussed. We are going to continue our discussion. We are going to continue our discussion on effect of change in frequency on photoelectric current as well as stopping potential, kinetic energy of emitted electron and so on. So मान लो for a given intensity of incident radiation we will make intensity constant, right? मान लो कि intensity कोई constant है, right? And current is flowing to the सर्किट जो हमने लास्ट लेक्चर में ड्रॉ की थी, राइट? सो फॉर गिवन इंटेंसिटी सम करंट इज फ्लोइंग टू द सर्किट. अब हम क्या करने वाले हैं, वी आर गोइंग टू चेंज द फ्रीक्वेंसी ऑफ इंसिडेंट रेडिएशन. हम अलग अलग फ्रीक्वेंसी के लिए वी आर गोइंग टू प्लॉट अ ग्राफ ऑफ फोटो इलेक्ट्रिक करंट वर्सेस स्टॉपिंग पोटेंशियल, राइट? बाय कीपिंग इंटेंसिटी ऑफ इंसिडेंट रेडिएशन सेम. जो इंसिडेंट रेडिएशन है उसकी इंटेंसिटी हम कांस्टेंट रखेंगे, राइट? बट वी आर गोइंग टू चेंज द फ्रीक्वेंसी ऑफ इंसिडेंट रेडिएशन. क्लियर? सो हम क्या करने वाले हैं, वी आर गोइंग टू प्लॉट अ ग्राफ ऑफ फोटो इलेक्ट्रिक करंट वर्सेस स्टॉपिंग पोटेंशियल फॉर डिफरेंट फ्रीक्वेंसी ऑफ इंसिडेंट रेडिएशन बट कांस्टेंट इंटेंसिटी. क्लियर? तो ऑलरेडी हमने एक ड्रॉ कर लिया था लास्ट वीडियो लेक्चर में. वी हैव ड्रॉन दिस बट अगेन वी विल ड्रॉ दिस. Let us say intensity is I, intensity I which is constant. हमने intensity को constant रखा है, ठीक है? So if intensity is constant then it was found that photoelectric current will also be constant. यहाँ पे जो है that is photoelectric current, right, versus stopping potential. Now for frequency f1, for a particular frequency f1 the stopping potential was found to be V01. Let us say this is for frequency f1. Now for frequency f2 the stopping potential was found to be V02 for frequency f2, and for frequency f3 the stopping potential was found to be V03 for frequency f3. That is, here you should remember that f1 is greater than f2 and f2 is greater than f3. We are increasing the frequency and stopping potential also increases, and here you can say that V03 is greater than V02 and it is greater than V01. This we have already discussed. It simply means that, right, from this graph we can say that as you increase the frequency of incident radiation stopping potential also increases, right? जैसे जैसे हम frequency increase करेंगे the stopping potential will also increase. What does this means? इसका simple meaning ये है कि as you increase the frequency the kinetic energy of emitted electron will increase, and therefore to stop these electrons we require more retarding potential, right? Potential को हमें increase करना पड़ेगा. The retarding potential must be increased to stop the electrons reaching the collector. Clear? This we have already discussed in our last video lecture. Now we are going to plot a graph of frequency versus stopping potential. ये जो graph था that was photoelectric current versus stopping potential by keeping intensity of incident radiation constant and changing the frequency. Now we are going to plot the graph of frequency versus stopping potential, right? So if we plot a graph of frequency versus stopping potential then the graph will be something like this. Let us say this is frequency, and here we have stopping potential. For two different metals we are going to draw, right? So for metal 1 the graph will be something like this. Let us say this is for metal A. This is stopping potential, F0 A for metal A, and for metal 2 or B this is for metal B, and here we will write F naught B. What is F naught A and F naught B? We will discuss. So if we plot a graph of stopping potential versus frequency for different metal, then this kind of graph we will get, right? So from this graph we can see that V naught, that is the stopping potential, varies linearly with the frequency of incident radiation. Stopping potential varies, let us write, from the graph of frequency versus stopping potential, we can say that number one, the stopping potential V naught varies linearly with the frequency of incident radiation. Right, stopping potential V naught varies linearly with the frequency f of the incident radiation. You can see that a graph of stopping potential versus frequency is a straight line graph, right? So the graph of stopping potential versus frequency, or frequency versus stopping potential, here we will write, is a linear graph, that is, it a straight line graph, right? So you can say that the stopping potential varies linearly with the frequency of the incident radiation for a given photosensitive surface. For a given photosensitive surface. So for a given photosensitive surface, the graph will always be a straight line, that is, stopping potential varies linearly with the frequency of incident radiation, right? Now from this figure, this F naught A and F naught B we will discuss. You can see that for frequency F naught A for metal A and for frequency F naught B for metal B, right, stopping potential is 0. Stopping potential is 0. So we can say that there exists a certain minimum cutoff frequency F naught for which the stopping potential is 0. Second point, we can say that there exists a certain minimum, it is known as cutoff frequency, which we have called as threshold frequency. There exists a certain minimum cutoff frequency F naught. For metal A it is F naught A, for metal B it is F naught B. There exists a certain minimum cutoff frequency F naught for which the photoelectric, for which the stopping potential is 0, right? So there exists a certain minimum cutoff frequency for which the stopping potential is 0. So from these two observations we can say that, let us summarize this. From the two observations we can say that, चलो what we can say discuss करते हैं, but before that first let us fast discuss this again. इसको थोड़ा रिवाइज कर लेते हैं. Stopping potential varies linearly with the frequency. अगर आप frequency increase कर रहे हो, you can see that as you keep on increasing the frequency, stopping potential भी increase हो रहा है, right? So it means that जैसे ही आप frequency change करोगे, stopping potential will change linearly. That's why we are getting a straight line. So linear change होगा. Now F naught or F naught A or F naught B, or F naught is a certain minimum frequency. कोई particular minimum frequency है, for that जो stopping potential है वो 0 है. Clear? So ये ग्राफ के दो observations है. Now these observations can be further simplified. Based on this graph हम कुछ और observation लिख सकते हैं, right? We can make some new observations from this. That from two observations we can say that, what we can say, the maximum kinetic energy of a photoelectrons varies linearly with the frequency. जैसे स्टॉपिंग पोटेंशियल इंक्रीज हो रहा है, राइट. सो लास्ट लेक्चर में वी हैव डिस्कस दैट के मैक्स, वी हैव डिस्कस दैट मैक्सिमम काइनेटिक एनर्जी ऑफ फोटो इलेक्ट्रॉन्स इज ई वी नॉट. नाउ जैसे ही फ्रीक्वेंसी चेंज कर रहे हो, इंक्रीज कर रहे हो, देन स्टॉपिंग पोटेंशियल चेंजेस और इंक्रीजेस. इट मीन्स दैट काइनेटिक एनर्जी विल ऑल्सो इंक्रीज लीनियरली. Just you have to multiply stopping potential by charge of electron, so that will be kinetic energy. So this is constant, so kinetic energy is directly proportional to stopping potential, we can say, and stopping potential is directly proportional to frequency. So we can thus say that the maximum kinetic energy of emitted photoelectrons varies linearly with frequency. राइट. हमने ऑलरेडी वो ग्राफ में देखा है कि फ्रीक्वेंसी इज डायरेक्टली प्रोपोर्शनल टू स्टॉपिंग पोटेंशियल और स्टॉपिंग पोटेंशियल इज डायरेक्टली प्रोपोर्शनल टू फ्रीक्वेंसी. कुछ भी लिख सकते हो, राइट. सो एज यू इंक्रीज फ्रीक्वेंसी, स्टॉपिंग पोटेंशियल विल ऑल्सो इंक्रीज. सेम वे में काइनेटिक एनर्जी की फॉर्मूला क्या है? काइनेटिक एनर्जी इज ई वी नॉट. So E is charge which is constant. So kinetic energy is also proportional to stopping potential, you can say. तो जैसे ही हम फ्रीक्वेंसी इंक्रीज करेंगे स्टॉपिंग पोटेंशियल इंक्रीज होगा. सो स्टॉपिंग पोटेंशियल इंक्रीज हो रहा है तो काइनेटिक एनर्जी भी इंक्रीज होनी चाहिए. सो हेंस वी कैन से दैट विद द चेंज इन फ्रीक्वेंसी kinetic energy will also change, or you can say that maximum kinetic energy of emitted photoelectrons varies linearly with the frequency of incident radiation. Of incident radiations, but it is independent of intensity of incident radiation, right? So the maximum kinetic energy of emitted photoelectrons varies linearly with the frequency of incident radiation, but it is independent of its intensity. That is, on changing the frequency, stopping potential and kinetic energy will change, but you can say that on changing the frequency, that is, we can say that the maximum kinetic energy of emitted photoelectrons depends on the frequency of incident radiation and it is independent of its intensity. Clear? Now the second point is somewhere over here we will write. Now the second point is, look, we have discussed that certain minimum frequency is required for emission of photoelectrons, right? Now for the frequency lower than certain minimum frequency f naught, right? For the frequency lower than certain minimum frequency f naught, even if the intensity is very high, photoelectrons will not be emitted, right? अगर हमारी frequency जो incident radiation की है, it is less than certain minimum required frequency और intensity is very high, then also it is found that जो photoelectrons है वो emit नहीं होंगे. Means इंटेंसिटी चाहे कितनी भी हाई रख दो, वी रिक्वायर सर्टन मिनिमम फ्रीक्वेंसी. अगर उस फ्रीक्वेंसी से द इंसिडेंट फ्रीक्वेंसी इज लेस तो फोटो इलेक्ट्रॉन्स एमिट नहीं होंगे, राइट. सो लेट अस राइट दिस सेकेंड पॉइंट. For the frequency f lower than or less than f naught, for the frequency f lower than certain minimum frequency f naught, no photoelectrons are emitted even if the intensity even if the intensity of incident radiation, even if the intensity of incident radiations is very high, अगर हम इंटेंसिटी को हाई कर भी दे but the frequency is less, then photoelectrons will not be emitted. Clear? Pause this video and copy this. Now यहाँ पे जो मिनिमम कट ऑफ फ्रीक्वेंसी जो रिक्वायर्ड है, राइट, दैट इज नोन एज थ्रेशोल्ड फ्रीक्वेंसी. यहाँ पे कहीं पे लिख देते हैं द मिनिमम कट ऑफ फ्रीक्वेंसी, और दिस कट ऑफ फ्रीक्वेंसी, this cutoff frequency f naught is known as, it is known as threshold frequency, right. So इसका मतलब ये हुआ कि अगर frequency of incident radiation is less than threshold frequency, photoelectrons will not be emitted. In order to get emission of photoelectrons, the frequency of incident radiation must be either equal to और ग्रेटर देन थ्रेशोल्ड फ्रीक्वेंसी, राइट. अगर हमें फोटो एमिशन चाहिए, राइट, फोटो इलेक्ट्रॉन्स एमिट होने चाहिए फ्रॉम एनी सरफेस, देन द मिनिमम फ्रीक्वेंसी से जो फ्रीक्वेंसी इंसिडेंट रेडिएशन की है वो ज़्यादा होनी चाहिए, राइट. द इंसिडेंट रेडिएशन शुड हैव फ्रीक्वेंसी ग्रेटर देन दिस थ्रेशोल्ड फ्रीक्वेंसी. नाउ दिस थ्रेशोल्ड फ्रीक्वेंसी विल नॉट बी सेम फॉर ऑल द मटेरियल्स. अलग अलग मेटल्स के लिए, अलग अलग फोटो सेंसिटिव सरफेस के लिए थ्रेशोल्ड फ्रीक्वेंसी भी अलग अलग होगी. हमने ऑलरेडी एक लेक्चर में डिस्कस किया है, राइट, व्हेन वी वर डिस्कसिंग एमिशन ऑफ इलेक्ट्रॉन, राइट, कि अलग मेटल्स के लिए थ्रेशोल्ड फ्रीक्वेंसी अलग है. किसी के लिए विजिबल रीजन में है तो किसी के लिए इट इज इन अल्ट्रावायलेट रीजन, राइट. सो डिफरेंट फोटो सेंसिटिव मटेरियल रिस्पॉन्ड्स डिफरेंटली टू द लाइट. लिख देते हैं ये भी, different photosensitive materials, different photosensitive materials responds differently to light, right, differently to light. So different photosensitive materials responds differently to light. अलग अलग लाइट के लिए photosensitive surface will also respond differently. Say for example, मान लो हमारे पास एक photosensitive surface है, right? Then it depends on, its response will depend on the wavelength of the incident light. इसका जो response होगा that will depend on either wavelength or you can say frequency also. Wavelength या frequency of incident light पे dependent होगा. Say for example, अगर हम कॉपर की एक मेटल प्लेट कंसिडर करें, राइट, लेट अस से वी हैव प्लेट ऑफ कॉपर. नाउ इफ यू अलाउ यूवी लाइट टू फॉल ऑन इट, अगर हम उसके ऊपर यूवी लाइट इंसिडेंट कर रहे हैं, देन फोटो इलेक्ट्रॉन्स आर एमिटेड. इट विल गिव राइज टू फोटो इलेक्ट्रिक इफेक्ट और फोटो इलेक्ट्रिक करंट. ऑन दी अदर हैंड, उसकी जगह पे इंस्टेड ऑफ दैट यूवी लाइट अगर हम विजिबल लाइट इंसिडेंट करेंगे, देन फोटो इलेक्ट्रिक इफेक्ट विल नॉट बी सीन, राइट. So obviously wavelength of visible light and UV light or frequency of visible light and UV light are different, so it is responding differently. So अगर given photosensitive surface है, then also its response will be different with different light. It depends on the wavelength of light, right? So you can write that the same photosensitive material gives different response to the light. So you can say that the same photosensitive material, the same photosensitive, instead of material let us write surface, the same photosensitive surface gives different light of different wavelength, or you can call frequency if you want, right. So the same photosensitive surface gives different response to light of different wavelength. Let us write an example also. For example, UV light when falls on a copper surface or plate, let us write copper plate, gives rise to photoelectric effect, give rise to photoelectric effect, while or whereas visible light does not give rise to photoelectric effect, right? For copper plate, visible light will not give rise to photoelectric effect. On the other hand, UV light will give rise to photoelectric effect. एक बहुत ही important चीज जो ऑब्जर्व हुई, that was this photoelectric effect was instantaneous. Instantaneous का मतलब जैसे ही लाइट फोटोसेंसिटिव सरफेस पे फॉल होगी, within 10 raised to -9 second, the time required to get emission of photoelectron is less than or equal to 10 to the power -9 second. जैसे ही लाइट फॉल हुई तुरंत इलेक्ट्रॉन एमिट होगा, ठीक है. सो द फोटोइलेक्ट्रिक इफेक्ट इज स्पॉन्टेनियस, यू कैन से दैट. मोस्ट इंपॉर्टेंट पॉइंट, फोटोइलेक्ट्रिक इफेक्ट जो है वो स्पॉन्टेनियस है एंड इंस्टेंटेनियस. As soon as light will fall on the surface, photoelectrons will be emitted within 10 to the power -9 second, right? So I am not writing here. Okay, let us write. This is an important point. Photoelectric effect is spontaneous. That is, within 10 to the power -9 second of incident light or radiation, photoelectrons are emitted, right? 10 to the power -9 second में इलेक्ट्रॉन्स एमिट होना शुरू हो जाएंगे, right? So the process is spontaneous and instantaneous. Clear? Pause this and copy. At the end of this video lecture, let us quickly summarize the observations of photoelectric effect, experimental study of photoelectric effect, right? So we are going to discuss the summary of observations of photoelectric effect. Summary of observations of photoelectric effect, right? In this, the first one is quite simple. For a given frequency which is greater than the threshold frequency, photoelectric current is directly proportional to the intensity of incident radiation. मान लो एक कोई frequency हमें दी गई है, right? And that frequency should be greater than threshold frequency. ये जो frequency है वो threshold frequency से greater होनी चाहिए, right? In that case, it was found that जैसे हम intensity increase करेंगे, photoelectric current will also increase. Or if you decrease the intensity of incident light, photoelectric current also decreases, right? So let us write the first one. First point, for a given frequency f, where f is greater than f naught, means the frequency should be greater than the threshold frequency, photoelectric current is directly proportional. Photoelectric current is directly proportional to the intensity of incident radiations. It is directly proportional to the intensity of incident radiations, right? Right, this was the first point. अब जो second point है, for that, suppose we have a photosensitive surface. हमारे पास एक already photosensitive surface है, and frequency is also constant. हमने frequency भी constant रख दी है, right? Then it is found that the saturation current, right, the maximum current, depends on the intensity of incident radiation, similar to this only, but stopping potential is independent of intensity of incident radiation, right? So you can say that our second point is for a given photosensitive surface, for a given photosensitive surface and frequency, that is frequency is also given, means frequency be constant here. So for a given photosensitive surface and frequency, saturation current is proportional to intensity of incident radiations, but stopping potential is independent, right? Stopping potential is independent of intensity, but stopping potential is independent of intensity of incident radiation, right? ऑलरेडी हमने डिस्कस किया है कि फॉर अ गिवन फोटो सेंसिटिव सरफेस एंड फ्रीक्वेंसी स्टॉपिंग पोटेंशियल विल नॉट डिपेंड ऑन इंटेंसिटी. रिमेंबर, अगर हम फ्रीक्वेंसी इंक्रीज कर रहे हैं देन ओनली स्टॉपिंग पोटेंशियल इंक्रीजेस. अगर हम इंटेंसिटी इंक्रीज कर रहे हैं देन स्टॉपिंग पोटेंशियल विल नॉट इंक्रीज. क्लियर? सो दिस आर द 2 points. The third one is for a given photosensitive surface, for a given photosensitive surface, there exist certain minimum cutoff frequency, which is known as threshold frequency, below which no emission of photoelectrons takes place. No matter how intense the light is, right? So for a given photosensitive surface, minimum frequency is known as threshold frequency और cutoff frequency. अगर मिनिमम फ्रीक्वेंसी से फ्रीक्वेंसी लेस है इंसिडेंट रेडिएशन की, देन अगर लाइट की इंटेंसिटी कितनी भी हाई होगी देन ऑल्सो फोटो इलेक्ट्रॉन्स आर नॉट एमिटेड, राइट? बहुत सिंपल पॉइंट है. फॉर अ गिवन फोटो सेंसिटिव सरफेस देयर एग्जिस्ट अ सर्टेन मिनिमम फ्रीक्वेंसी, कुछ मिनिमम फ्रीक्वेंसी होगी, राइट? अ पर्टिकुलर मिनिमम फ्रीक्वेंसी इज देयर फॉर ईच फोटो सेंसिटिव सरफेस. और अगर इंसिडेंट रेडिएशन की फ्रीक्वेंसी इस फ्रीक्वेंसी से लेस है, then no matter how high the intensity is, photoelectrons are not emitted from it. Clear? Photoelectrons नहीं emit होंगे उसमें से, right? But if the frequency is greater than threshold frequency, then with the increasing frequency, right? With the increase in frequency, the stopping potential will also increase. यहाँ पे हमें add करना है, which I am not going to write. You can write yourself. Just I will dictate it. अगर हम फ्रीक्वेंसी इंक्रीज कर रहे हैं बियॉन्ड थ्रेशोल्ड फ्रीक्वेंसी से हमारी जो रेडिएशन है उसकी फ्रीक्वेंसी हायर है, देन जैसे आप फ्रीक्वेंसी इंक्रीज करते जाओगे ठीक उसी अमाउंट में डायरेक्टली प्रोपोर्शनल टू, राइट, स्टॉपिंग पोटेंशियल भी इंक्रीज होगा, राइट? सो विद द इंक्रीज इन फ्रीक्वेंसी स्टॉपिंग पोटेंशियल विल ऑल्सो इंक्रीज. एंड हेंस यू कैन से दैट काइनेटिक एनर्जी जो एमिटेड इलेक्ट्रॉन्स की है वो भी इंक्रीज होगी. क्लियर. सो विद द इंक्रीज इन फ्रीक्वेंसी अबव थ्रेशोल्ड फ्रीक्वेंसी, stopping potential as well as kinetic energy of emitted electron will increase. Fourth point, which is most important one, fourth point here, as soon as the light of frequency f, where f is greater than f naught, falls on photosensitive surface, as soon as this falls on the photosensitive surface, photoelectrons are emitted. Photoelectrons are emitted. Right. As soon as means we have already discussed, that is within 10 to the power minus 9 second of incident radiation, right? Within 10 to the power minus 9 second of incident radiation, photoelectrons are emitted. Means जैसे ही light surface पे fall होगी, with no time lag, electrons will be emitted from it. Photoelectrons will be emitted from it. Remember, even if intensity is very small, अगर light की intensity is close to zero, but frequency is greater than stopping potential, frequency is greater than threshold frequency, but frequency is greater than threshold frequency, then also photoelectrons will be emitted within 10 to the power minus 9 second. Clear? So this is a summary for photoelectric effect, experimental observation of photoelectric effect. Clear? In our next video lecture, we are going to discuss about the difference between the wave theory and the photoelectric effect, right? What is wave theory and how it fails to explain photoelectric effect, that we are going to discuss in our next video lecture. Along with it, we are going to discuss Einstein explanation for it, for the photoelectric effect. Remember, Einstein got Nobel Prize for explaining photoelectric effect.